Hi everyone, and welcome to another episode of Mr. Carlson's Lab. I'm still patiently working on the Vitalizer project at this time. What an incredibly time-consuming project this thing is turning out to be. It's like the project that never ends. So in the meanwhile, I have lots of smaller projects that hit the bench, and I'm going to share some of those projects with you while I'm working on this Vitalizer. So today we're going to take a look at a Sansui B-77 stereo power amplifier. There's a problem with the spectrum analyzer display that we're going to fix together. So I'll get the amplifier on the bench and we'll get started. Here you are, sitting at the bench at Mr. Carlson's lab, viewing this Sansui amplifier the exact same way I'm seeing it right now. So the amplifier is a Sansui B-77 stereo power amplifier, and the complaint is in the spectrum analyzer display, which is right here, and we'll take a closer look at that in just a moment. So what's happening is there's a row of bars that's lit from end to end on that display, and that's not supposed to be like that. So if you were to purchase an amplifier like this and say you didn't have a chance to play with any of the buttons, you could think that that's some form of a level set or something like that, but you'd quickly learn that there is a problem in the display. So the complaint is a row of bars lit, and there's actually a row of bars that doesn't light following this. And we'll take a look at that here in just a moment. So the display itself that we're going to take a look at here is known as a vacuum fluorescent display, or in short VFD, and really what it is it's a vacuum tube, just like the vacuum tubes that you find in older radios. They have filaments and a cathode and a grid and a plate, just like a vacuum tube. These are still very common. They're used in lots of stereo equipment and home entertainment stuff today even. They have a really nice look about them. That's why they keep using these things. So this is pretty early. The B-77 is 80s era, something like that, but it's still a very nice amplifier. So what I'll do is I'll turn the power switch on. I have this thing attached to my isolation transformer, variac, and current limited supply right now, just in case there was something else to go wrong with this. But supposedly, this is the only problem. And as you can see, there is a row of bars lit, and I just heard the click from the protection relay, which is always a good thing as well. So it's not supposed to do that. So what I'm going to do is I'm going to hook up an audio source to this, and we'll take a closer look at that display. So I'll just hook up some random music that'll be quiet. You won't hear it, but you'll see the display bounce around and things like that, and we can see what's actually going on with the display itself. Okay, let's take a look at what this display is doing. So I'll give this a little bit of volume here. This is on the lower power setting. So you can adjust the display power level right here. No, that's not hitting 100 watts right now. So you can see that there's a row of bars lit, and you can see that they're kind of jumping above little row of bars here that's missing. So, interesting issue. So that's the problem that we need to look for right now. It's nice that this display is working okay. It's just this is the issue in here right now. And as we can see, both channels are working just fine, and they're pretty even as well. So that's nice. It pretty much isolates the display section. So let's get inside this thing and make it work again. The power has been removed from the amplifier, so the amplifier is unplugged. And in order to get into the spectrum display, we need to get the top off of this thing. So if we look right here and here, that appears to be the only two screws that we need to remove to get inside. So let's just do that right now. Okay, so here we go. Well, that's nice and easy. So what I'll do is I'll move in the camera a little bit closer and safely discharge the capacitors in here so it's safe to be poking my hands around, and I'll be right back. Before moving your hands around in an amplifier like this, or moving a screwdriver around or a probe or anything like that, it's very important to make sure that the amplifier, or DUT, which is short for device under test, is disconnected from the AC line. So you want to make sure that what you're working on is unplugged from the wall, just because it's very dangerous. And the further you go back in years, the more dangerous the equipment is inside, and I'll explain a little bit more about that here in just a moment. In this video, I'm going to show you how to troubleshoot circuitry without having it powered up. So there's a very neat little piece of test gear that you can build yourself that'll very quickly locate bad components without even having a schematic. It's a really neat little piece of gear, and not a whole lot of people know about this. It's also very important to make sure that the capacitors in the amplifier or device under test, whatever it happens to be on your bench, are discharged as well. Those two very large capacitors that you see in the back there can hold a lethal charge. And here's the thing, if they're not discharged correctly, you can damage the amplifier as well. So in many of these amplifiers, one capacitor is for the positive supply and one capacitor is for the negative supply. If those aren't discharged correctly, you can damage the amplifier. So in order to help discharge capacitors a little easier, I've designed this box here, and I've released this on Patreon with all the plans for the circuitry and schematics and everything. So this helps discharge capacitors much easier and in a much safer way as well. So you can see there's two probes here, and if you're to go across the capacitor like this and discharge the capacitor like this, or like this, so you can reverse the probes, it doesn't matter. There's an LED that will indicate the discharge in either direction, and if that's not enough, there are some carry-through leads that you can run to an external voltmeter, and you can actually watch the voltage fall on an external voltmeter. So the device itself is all isolated inside this box. You can even see there's plastic screws holding the circuitry and standoffs away from the box itself. So this is designed to be a safe discharge unit. I use this thing all the time. Very important piece of equipment to have on your bench. Probably one of the most important pieces, especially when you're working on stuff like this. Now, as I explained earlier, the further you go back in years, it's almost like the more dangerous this stuff gets to work on. You can see here that on the top side of the transformer, there's a whole bunch of exposed wires, and they use the wire wrap system here. What you see right here is exposed AC line. And as you can see, if I tip the amplifier up just a little bit, you can see that, they're really long. So they almost stick out of there like pins. And if you were to come across this with your hand like this and touch the chassis while this was plugged in, you could receive a lethal shock. Now, as you can see, there's exposed AC all over here. The fuse is exposed. In the back where the two outlets are that you would plug your other stereo equipment into, you can see back here that the wiring is all exposed here as well. Nowadays, usually they have heat shrink on all of this stuff, so there is really nothing exposed from the AC line in most situations. But the further you go back in years, the more dangerous a lot of this equipment gets, right to the point to where you have one side of the AC line attached directly to the old radio receivers in the 60s and the 50s. So, from this, where things are getting isolated, to basically connecting one prong of the plug directly to the case. So as you go back, it gets a little bit more dangerous, and I talk a little bit about this in my other videos as well. And I'm going to do an entire dedicated safety video, going back in technology about this stuff, because a lot of people don't realize this. Like this here, right on the top, just like this. Exposed AC line right there. Extreme shock hazard. If that's not enough, there's more right here as well, right on this switch. They did use a safety cap. That's a nice thing. So amplifiers like this, I have to admit, Sansui, this company, had great engineers, and they knew how to design things properly, and they knew how to draw a schematic correctly. You don't see much of that anymore nowadays. This amplifier is very well designed, and it's really rare to see any of these older pieces of gear failing even today. We'll take a look at the schematic here in just a moment. We'll take a look at how they've drawn it, and I'll show you some signs of proper engineering, the way that engineers should be thinking today, instead of giving you a schematic and then obscuring things, by drawing things silly. Now, this has been going on throughout time, but again, the Sansui company, they were really good for drawing this, and, the engineers were out there to convey the information to the technician that was going to repair the amplifier so they could get it fixed in a timely manner. So I'll touch a little bit more on that here in just a moment. So keep in mind, if you're following along and you're working on an amplifier or anything, you're doing so at your own risk. Please take care. This is the display board that needs to come out so that we can service this. And the connectors on these older Sansui amplifiers like this are a little different than what you would find in a modern amp. What happens is you remove a little clip or fold it up and the wires actually come out. So the wires are bare and they just kind of get pinched in these clips. So it's very important before you service something like this and before you pull the board out to take note where the wires go, especially if there's a lot of these things on the circuit board. So I'll give you an example here. So what you do is you just pop this little clip up like so, all right? You can see these little things right here. Let's see if I can get my little pointer in here. You can see right here that what ends up happening is these little parts here wedge against, see the little things right here? They wedge against the little connectors in here and they pinch on the wire. So what happens is once you remove this, you can actually just pull the wires out just like that. So if you have a whole bunch of these things on a circuit board, again, it's very important to take some pictures, right? So remove this one here, just like so. And again, you can see why it would be so incredibly important to discharge all the caps, right? Because if you were to pinch these together and touch the wires, you could cause a lot of damage. There's one more over here. It's this side here. Let's remove this. Up here like so. And just like that. So I'll just put these in here. These are the filament lines anyway, so I'll just put them in here like so, and then that way I can remember which way they go. That's kind of handy. So now, in order to get the board out, it looks like we only have 2 screws here, so I'll just remove these 2 screws. And there it is. So I'll just get this out of the way and we'll take a closer look at the display board. Just before we get started in the troubleshooting procedure, let's take a look at their board. Admire their workmanship, so to say. They did a really nice job. For a single-sided board, they managed to keep all these transistors in a line, pretty much all in a line. The ICs are all facing forward. These ones here, at least, you can see the index here, here, and then here, 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 and then you can see a little dot here. This is forward and forward. These 2 ICs that are running this way, the index is here and here. So, they've done a really nice job in trying to keep this thing as clean as possible. And of course, if you're to bend all the capacitors up like so, you could really make it look nice. These things are put together so fast that, capacitors are laying over and sometimes transistors are soldered in crooked, things like that. But all in all, really, really nice design. Managed to keep a lot of the resistors in a line here as well. If we look at the bottom side, looks just pristine. Look at that. So nice and clean, no signs of tampering or anything. It's really nice to get stuff like this that, people haven't been in here and been reefing on things with pliers from the top side. Pads are missing and things like that. Nice and clean. A little bit of glue here on this connector. Look at that, just shines. It's nice to work on this kind of stuff. And on the front, we have a thing called a vacuum fluorescent display, or VFD. So this thing here is a vacuum tube, just like an old vacuum tube that you find in a radio. This here is the evacuation point where they pull the atmosphere out of the tube, and you can see the getter compound in the corners. So what this stuff here is a compound that they flash with high power RF. So usually they have a coil that they put over the corner here, and there'll be some loops under here. And they flash this getter compound onto the glass, and throughout the service life of this vacuum tube, these spots absorb the impurities inside the tube. Because as these things get hot and cold and hot and cold and things like that, these things, their parts inside tend to off-gas, so they let off impurities, and the job of these two spots is to take care of those impurities so the display glows throughout its service life. This is just like a standard vacuum tube. It has filaments. You can see these, they look like little strings here. Those are the filaments running across from side to side. These have grids and plates, just like standard vacuum tubes, and those ICs that we look at on the top control those grids and plates. These run at reduced voltages, so they don't run at the high B+ levels that a normal vacuum tube runs at, and these things are still very common in home audio gear today. These things are used all over the place. So vacuum fluorescent displays are usually blue. Sometimes they have multiple colors inside them, but most common blue. And they really do look quite nice. That's why they still use them even now with all of the LEDs and everything on the market, right? So that's the display, and back here we're going to have a bunch of drivers that are going to be driving this display and doing a bunch of switching and things like that. So what I'll do is I'll get this thing out of the way and we'll take a look at the schematic. This is the portion of the schematic that we're going to be taking a look at today. This is the display or indicator unit inside this amplifier. You can see that we have a dotted line around this circuitry on the schematic that indicates that this is a separate board within that amplifier. And we know that this is definitely a separate board. When I say that the engineers at Sansui were thinking and they really did a nice job on this schematic, the schematic really just reeks of quality. You can see on this side here we have a legend for all the components with the numbers here. You can see that they've written in the voltages for all of these areas on the entire schematic, and they've highlighted the voltages to make them easy to find. The entire audio signal path is red with arrows showing from input to output, so they're showing which way the audio is traveling. You can see down here we have signal line and we have negative feedback line. So the legend here is a straight red line is signal and a dotted red line is the negative feedback line. We're not going to worry about the negative feedback line because that's basically over here in the audio output section. So this is the area that we're going to focus on today because this is where the problems are. Now, if you were to troubleshoot this amplifier with power applied, so if there was AC applied, all of these voltages would be valid with no signal at the audio input jack, basically the amplifier just sitting there and idling. Today we're going to troubleshoot this section in a much safer method. We're going to use a thing called a signature tracer to locate the problems inside this amplifier. That allows us to troubleshoot this board standalone, no power applied. The signal tracer applies the power itself. So the signal tracer is a very handy piece of equipment to have if you have a piece of circuitry and you have no schematics available. So no schematics, signature tracer, you're on your way to success. That's the reason that I use one of these things all the time. It'll help me get through troubleshooting a circuit board with no information available, and it gets me through the troubleshooting procedure really fast. Again, signature tracers really aren't talked about a whole lot, but they really are that secret in the industry that gets quick results. So you'll see it operating here in just a moment. So whenever you see a vacuum fluorescent display tube like this, usually when you have a glowing line, there's a problem with the driving section for the tube. So I suspect already that probably one of these ICs here have a problem. So these are all little parts inside the ICs. So these are all comparators here. So one of these probably has an issue, and when we find that, we'll be able to fix that. Now, even if I didn't have a schematic available for this, whenever you're dealing with a vacuum fluorescent display or electroluminescent display or anything like that, whenever you have a glowing bar or something that's glowing on the screen that shouldn't be, usually it's a driver issue. So this here is really suspect. If we don't find any problems in here, we'll just work our way back just like that. will very quickly find the problem. It's very rare for the actual tube itself to fail. Usually when something goes wrong in these things, you'll see a sagging filament line or something like that in there, that will short to part of the display. But that is really rare unless, it's been, in a very rough environment. So as I was mentioning before, just like a normal vacuum tube, they have grids, plates, and a cathode. So you can see all of this here. It says P, 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 all the way down here. You can see all of these P's. These are all the plates inside the vacuum tube. You can see G for grid. These are all the grids inside the vacuum tube. And you can see F for filament. So F is the same thing as a cathode in a vacuum tube. This would be called a directly heated vacuum tube because the filaments themselves are acting as the cathode. The filament itself has an emissive coating on it. So if we look inside this vacuum tube here again, we already noted the filament lines over here. So we see these little things that look like strings running across. These things here are the cathodes, and they glow a very light orange color in service. And that's the reason whenever you see a vacuum fluorescent display, it usually has a tinted piece of plastic sitting on top of it. Usually the plastic is the same color as the actual display itself, so that it allows the color of the display to travel through that tinted piece of plastic with ease. But that piece of tinted plastic will block out the orange color from the filaments, because if you didn't have the tinted piece of plastic in a dark room, you might actually see the orange glow of these filaments. Now, these filaments have to glow orange in order to emit electrons. If these things don't glow orange, our display is not going to glow at all. Again, it's just like a normal vacuum tube, except you got to be a little bit tricky to get rid of the colors that you don't want. And orange, in this case, is the color that we do not want to see. So what I'm going to do now is I'm going to get this little display all set up with the curve tracer, and I'll show you exactly how to use a curve tracer. So this is a signature tracer or curve tracer. You can call it either or. We're going to use that to troubleshoot these ICs, and I'll show you exactly how to very quickly troubleshoot the driving ICs in here and find the problem. Lots and lots of ICs for us to test here. The first ICs that we're going to check are these JRC2901N ICs. So this one, this one, this one, this one. And since they didn't have enough comparators, they used an op-amp as well. So there's a 4558 over here. These are all directly connected to the display, which means that these are suspect first. If we don't see any differences in these, we'll just move on to other ICs. Now, the JRC2901N is really common. It crosses to the LM2901. You can see the similarities there. And also an LM339. Now, I have lots of LM339, so if any of these are toast, I'll just replace it with one of these. And I also have lots of 4558s as well. So what we want to do is use the signature tracer here to look for differences in these ICs. If we see anything that's dramatically different from another IC here, we would instantly place that IC as being suspect. So since all of these ICs here are wired into the circuit pretty much the same way, they're all of the outputs are all attached the same way. If one of the outputs or two of the outputs or more of the outputs look off, they don't look the same, then that places that component or components as being suspect. And that's how you use a signature tracer. It really is just that simple, and they're very effective. So you'll see here on this IC, this is the layout here, so you'll see pin 12 is ground. So I want to take the common lead right here of my signature tracer and attach it to ground. So that's a black lead here, and I'm going to use the red lead to probe the outputs, because the outputs are directly attached to that tube in the front here. So that makes these outputs suspect. So I'll touch the red probe to 1, 2, 14, and 13 while keeping the black probe on pin 12. And we're going to look for similarities in these ICs. Now, these ICs are designed to pull down, whereas an op-amp has two transistors in the output stage, so we're going to have a different signature for these two 4558s than we are going to have for these JRC2901Ns. So these should look just like diodes, and this will have a Zener diode type of look to it, and I'll explain that as we're going along. So I'll just start with this one because it's in the center. So I'll put this to pin 12. Okay. So now what I'm going to do is attach this to pin 1, and we should have what looks like a diode. And there it is. So we'll go to pin 2. Looks like a diode. And we'll go to pin 14. Looks like a diode. And we'll go to pin 13. And it looks like a diode. On to the next IC. Let's go over here. Again, to pin 12, the black lead to pin 12. 1 looks like a diode. 2 looks like a diode. 14 looks like a diode. And 13 looks like a diode. Let's go to this one here. 1 looks like a diode. Pin 2 looks like a diode. Pin 14 looks like it probably has some issues with leakage. And pin 13 is not looking too bad. So already I see a problem. So right now, that places this IC as being suspect. So let's work our way back over to this one here. We worked our way over to here. Actually, let's take a look at this 4558 first. So pin 8 is ground on the 4558. They actually have it nicely listed right on their sheet here. So pin 4 is ground, and we want to take a look at pin 1 is the output, and pin 7 is the output. So output A and output B. So we'll take the ground lead of the curve tracer and attach it to pin 4. And we'll take a look at pin 1, and we should have what looks like a Zener. And as you see, the little curve in the center, that's looking okay. Now if I go to pin 8, or is it pin 7? It's pin 7. We have much the same look. So I'll go down here and test this one over here, and we should have what looks to be pretty close. So pin 7, there it is. And pin 1, there it is. No problems. So far, this one here is looking very suspect. So let's test this one over here. This is the last one for us to test. I'll take this lead here and put it here. So we'll look at pin 1. Pin 1 isn't looking very good on that at all. Pin 2, same thing. Let's look at this one here. Not looking good. So that's looking like these are beginning to leak. So these two here looked really good. This is how it should look. All right. So that's how it should look right there. It's nice and solid, right? And that's pin 2, pin 1. I'm just moving it from in between the pins really quick. 1, 2, and then we'll go pin 14, pin 13. That's how they should look. So these ones here are starting to look leaky. You can see it has a bit of a curve at the end there. Yeah. So to me, that places both of these ICs as being suspect. They shouldn't look like that. So what I'm going to do is I'm going to replace both of these ICs right here. This one here looked like it had maybe, 3 parts in it looked okay? I think it was 3. So we got, yeah, that looked okay. 1, 2, and then I think it was this one here. It looked not bad, yeah. And then, of course, we have this one here, which is really looking bizarre. So what I'm going to do is I'm going to heat up my desoldering tool. I'm going to pull both of these things out, replace them with LM339s, and then we'll try this board out and see if that yields any results. The two ICs that we want to remove are these two right here. So I'll just turn this upside down like so. That's this one here and this one here. So I'll take the desoldering tool. So that IC is out of there. So what I'll do is I'll pull out the other one in the exact same manner, and I'll put the new ICs in and we'll give it a try. The two new ICs are installed, and this is pretty much ready to get reinstalled back into the amplifier again. So what I'm going to do is clean up the VFD. It looks like there's some fingerprints and stuff on there, probably from me. See some smearing on there and stuff. So I'll clean this off with some Windex, and I'll also clean off the inside of the window on the amplifier as well. So clean that all off and put this back in, and we'll give it a try, see if it works now. The indicator board is reinstalled back into the amplifier. That really goes quite quick, just 2 screws, and then put these wires back into the connectors. When you're putting these back in, you also want to make sure that you don't get 2 of the wires together and press down into one of the connections here. You want to make sure that all the wires are separate and they go to their individual connections. That could very easily happen if 2 of the wires get squished together and put down in the same one. And that would short something out in the amplifier, so something to take note of. So everything is reinstalled back into the amp here, and we're ready to try it out. So I'll reposition the camera, and we'll see if the spectrum display works again. Okay, the moment of truth. Let's see if the display works. Here we go. Well, we don't have a line, and I did hear it click, so that's a good sign. So here, I'll give it some audio. It's looking good so far. Look at that. That's looking the way it should. Looking very nice. The display is nice and bright. It's working very well. So you can see how quick and easy that signature tracer made finding this problem. And it's like that with all sorts of electronics. Really is a useful tool to have on the bench. I use the thing all the time. If you think a piece of test equipment like this would benefit your workbench and make you a more efficient troubleshooter, you're definitely going to want to check out my Patreon page. All the plans to build this are there, so all the circuit board layouts, schematic diagrams, and there's even example videos showing how to test circuits with this device. I have to be honest with you, this thing really is a great thing to have on the bench. I use this all the time for working on switch mode power supplies and amplifiers and all sorts of things. So when I designed this to go well beyond just being a signature and curve tracer. At these jacks here is a very low distortion sine wave output. So it's using a very low distortion sine wave to test components. The distortion is so low that you can use this thing to test audio amplifiers with. So you can actually take the signal right off these jacks and feed it into an audio amplifier. There's a 1000 cycle signal available right here. Now, other devices like this that are on the market, if you've looked these things up, they're extremely pricey, and usually they have fixed ranges. The range on this is continually variable. So there are no fixed ranges, which makes this thing extremely versatile. Not only that, there's a cable that runs out of the backside that you can attach to a digital voltmeter, and that gives this an external digital display, so you can look at the forward and reverse of diodes and things like that as well. So the list goes on and on. It really is quite a versatile device, and I spent quite a bit of time designing this thing and trying to perfect it and make this thing work just the way it does, and I'm extremely happy with the results. I've shared this up on Patreon with all the patrons, and many people have built this and they're enjoying this project themselves. So very, very good thing to have on the bench. So definitely feel free to go up there and check it out. Thanks for stopping by the lab today. I hope you enjoyed this very different type of troubleshooting procedure that I've shared with you. If you did enjoy the video, you can let me know by giving me a big thumbs up and hang around. There'll be many more videos coming like this in the near future. We'll be troubleshooting, repairing, restoring all sorts of different electronic gear, solid state and vacuum tube alike. So if you haven't subscribed, now would be a good time to do that as well. If you're interested in taking your electronics knowledge to the next level and learning electronics in a different and very effective way, you're going to want to check out my ongoing electronics course on Patreon. I'll put the link just below this video right at the top of the comments section. So I'll pin the comment. All you need to do is click on the link and it'll take you right there. All right, until next time, take care. Bye for now.